Can you recall who the person on the screen is? Now? Yes, you guessed it right. The man is Leonard Paul Euler, and the equation in front of you is the much famous Euler's identity, e power I pi is equal to -1. But what was this hell of a genius doing when not immersing himself into the intricacies of the world of complex numbers? Well, this is one problem he was juggling with. What you see is a map of the city of Königsberg, a port city on the Baltic Sea with the river Pregel flowing through it. And here is a more simplistic view of the city as it existed during Euler's time. The two islands were connected with each other and with the mainland by 7 bridges, their relative positions as given in the diagram. The task before Euler was to cross each of the bridges once and only once, starting from any piece of land of one's choice. Rule of the game is each bridge must be crossed completely. One is not allowed to travel half a bridge from one side and the other half from opposite side. Euler started by making an important observation. The choice of a traveler's route on the landmass was irrelevant. So, each landmass might as well have been a point for good. The bridges joining the landmasses can be considered as edges joining these nodes. The equivalent task now is to start at a vertex and travel each edge exactly once. Corresponding to each edge used to reach any particular node, we need an exit edge to come out of that landmass. The other possible exit edges for the green entry edge to this node are the ones being currently flashed on your screen. As you can see, every path through a vertex involves a pair of edges connected to it. What this means is, except for the starting and ending points of a journey, all other vertices should have an even number of edges connected to them if we want to travel each of the edges exactly once. As some amongst you might be wondering by now. Yes, the conclusion is that the given task is impossible. Yeah, you heard it right. Since all the vertices of this graph have odd number of edges connected to them, we cannot travel all the edges without traveling any of them twice. Does all this fuss remind you of something more familiar? The ubiquitous high school challenge you throw to outsmart a classmate. Such interesting problems and questions constitute the subject matter of the area known as graph theory. And just in case you were thinking it to be a child's play, the theory finds its applications in areas as diverse as transportation, biology, chip designing, chemistry, and guess what? Even our understanding of social networking.